Welcome everybody. It's 3 o'clock Central European time, the start of our webinar, TVS production diodes from 1 nanoseconds to 400 milliseconds. And we'll also talk about new technologies like Foldback Technology here. A couple of housekeeping rules before we start. After this webinar, you will receive an email from us, with information about the presentation and things like that. Also, we're actually going to make a recording. And so this recording actually will be made available in case I get carried away and speak too fast, or you want to listen to certain things again. That will also be made available. After the webinar, there will be a question and answer session here. There's a function here where the questions function here where you can put your questions here. And after this webinar, we'll actually try to answer them. Don't worry, those questions will not be lost if you are actually don't get an answer or anything like that. They are recorded and you will be answered via email here. The time of the webinar, we think it will take about 45 minutes here. So here we go, and let's go to the first slide with the agenda here. As we advertise the webinar via Bodo's system design, maybe not everybody knows us, so 2 foils about our company. Then we're going to talk about transient TVS diodes. We're first going to focus about transient thermal resistance and thermal resistance, the difference, and how that impacts your design and the components you're choosing. Automotive pulses tend to be a little bit more different, so we're going to talk about testing them here. We're going to talk about Foldback Technology, the new technology which we've announced here. Then we're going to talk about packages, the different packages available, and how you choose the correct package for your application, or at least to try to help you a little bit with that. And we're going to give you a little bit more applications information about TVS diodes. So that's the bulk of the webinar. We're also making some ESD components, and we're going to talk about them too. And we're going to talk also about the Zeners and also the front end and the supply chain of these products, because we don't want to live 100% in a technical vacuum. So here we go, 2 slides about our company. One slide, I'll let you read that slide by yourself. These are the basic data about our company. While you do so, I would like to mention that we are 20 years in Europe, and so we have salespeople here in Europe. We also have customer service, logistics, warehousing, and we also have an automotive quality specialist, and we have also technical support here. That's where I work. My name is Jos van Loo, and I will be your host today. Taiwan Semiconductor actually is known for rectifier and protection diodes. That's our core business, and that's what we really focus upon here. We're also recently started or not recently, more than 5 years, a bigger MOSFET design team where we have automotive qualified MOSFETs here, and we invest actually also in the MOSFET backhand internally here, and we have a partner that's on our board, UMC here. So those are our critical product groups here. We also make a number of other components to complement this here. And the second slide is missing, but we also have a design team for linear regulators and LED drivers here that can also be delivered automotive AEC-Q qualified. The company is focused on automotive semiconductors here, and the majority of our products are automotive qualified. Let's go to transient, the TVS diodes, and let's go and jump into the technical details. Before we do so, one simple graph here, the voltage current curve, and just to give put the 3 technologies we're discussing today in perspective here. So you have the traditional TVS here on the far left here, with the breakdown voltages ranging from very low to very high here, and actually the current or the power dissipation in this product is actually very high. They are measured using 10/1000 pulses here, so longer pulses here with very high currents here. So those are main protection devices versus longer surges, and also on steady state applications here. Zener diodes tend to be more as a voltage regulator function, where the currents are low, probably even much lower than 100 milliamp. We're showing in our graph here in green here, and they also have a lower voltage. The majority of the Zener applications are very low voltage here. And then ESD, specifically the low energy components here, used in IOs interfaces all the time here, where actually the current here is the transmission line pulse current at 30 amp, where it's characterized, or are different currents here, and obviously those are very low power applications. applications here. So those are the three groups we manufacture. The bulk of the information today is going to be about TVS applications. So how to choose a TVS diode here, and now we're going to go to the technical stuff here. We have the clamping and the working voltage. Those were on the previous slide. I didn't really highlight them, but I hope they understand here. Working voltage is the area where the TVS is transparent to the system. The clamping voltage is the worst case voltage you can actually get or expect here, and everything behind the clamping voltage here, behind the TVS, has to withstand that clamping voltage, otherwise there is destruction here. We also have to take into account robustness and power, capacitance, and the cost and the supply chain. So we actually give you a complete picture of these things. How to choose a TVS diode actually will depend on the pulse you're actually protecting against, and also that is important from a technology perspective. So if you have an ESD pulse, actually the only thing that is what's going to be important is going to be the capacitance, and also maybe the package and the layout of your system here. If you're going to the medium-sized pulses, which are, we call the lightning strike pulses, 820 or 101000 or 10700, or the ISO pulses for automotive specifically, actually, if you're looking at that here, the thing that is actually determining the performance of the TVS diode is the die size, the silicon itself here. If you're going to low dumps and longer pulses, actually, you're starting to talk about 40 milliseconds to 400 milliseconds. It's not just the die itself, but everything surrounding the die and the lead frame design and that type of stuff. So it's a very complex picture here. So that's why testing for those type of products is still important here. A lot of TVS diodes are used in a steady state situation here. Steady state means that there, let's say, a clamp circuit over in a flyback transformer, and you're protecting the 600 volt MOSFETs, and you need something that actually has a duty cycle of 1 or 2% here to make sure that the 600 volts or whatever process voltage is not exceeded here. This has steady state power dissipation here. And there are also other clamps on MOSFETs between, for example, drain and source, gate and drain, and other clamp circuits all over in the business, including freewheeling here. In that case, actually, the defining factors are going to be your package and your PCB layout. Let's talk a little bit more in detail about all these pulses and everything that influences them. Underneath here is, you can see that all the pulses tend to be very well normed here. So that is actually an advantage here. But we'll talk a little bit about norming and how accurate that norming is a little bit later on, maybe. Here we go. The first one actually we're going to look at here is the SMA6F, as you see in the title here. On the left, we have the steady state power rating, depend on the thermal resistance. On the left, you have the rating for pulse power, the 600 watts in this case, which is transient thermal impedance based. What is the difference between these curves? The SMA6F is a 600 watt thin SMA type products here. If you are using this in a steady state, like, clamp, freewheeling, that type of application here, it's just the way any semiconductor works here. The maximum junction temperature is 175 degrees C. You reach that by multiplying the power dissipation with the thermal resistance here. And of course, you would like to have this temperature below the maximum junction temperature here of the product, preferably also a little bit lower here, because Arrhenius and fit data apply, and you really want to have the lowest possible junction temperature for your design here. The second one on the right is a completely different animal here. What you see here is that on the far right hand side here, you see that at 175 degrees C, the device can still actually dissipate around 400 watts. That refers to a 101,000 pulse here. What does that mean? Well, the first thing, if you think about it, obviously, is that the junction temperature is going to be exceeded. And this is actually quite common with pulses, with short pulses here. The junction temperature can be exceeded here. The second thing is that we actually supply this graph upon request, because it's usually okay or better to help or guide the customers understanding these graphs here. We've seen a webinar recently of one of our competitors here claiming that their parts were better, and they were comparing the thing in the right-hand side to the graph in the left-hand side. Well, actually, that is not comparing apples to apples here. The one on the right-hand side is basically for single pulses. We also get sometimes questions for people, and we do supply Cower models. They're not always on our website, but you can always request for them, and we will supply them to you. Cower models are not the best way to simulate some of these pulses. What you're essentially doing is you're simulating the melting point of silicon, and that's a bit dangerous here. So we would like to keep you a bit away from using Cower models to work with single pulses here, or at least help you interpret how it works here. So that is the first thing we would like to say here. If you're steady state, you're a completely different situation than when you are in a short pulse here when it comes to actually to rating. And that is sometimes not always understood in the business. The second graph here is about the package choice or the package downside. We actually today here, we actually introduced, and I have a small typo in the thing, this is an ASLD 123 package here. So we today introduced this newsletter on our website, and last week we produced the device, or last month we introduced the device here. So you can see both are rated at 400 watts here. Both are, of course, ACQ 101 qualified here. The SMA, the SOD123W, let's make it easy. It's 50% or half the PCB stays of the SOD128 SMA here, and actually their height is more than also reduced than half here. Less than 1.1 millimeter versus 2.5 millimeter here. On the title of the distribution of this webinar, we said that some surface mount TVS diodes already exist 35 years here. And actually I refer to the SMB, which is the first package that was, if I remember well, introduced in the market here. The SMB actually here, or the SMA here, if you look at the design, it's very simple. You just look at the side drawing, the side view here. The blue thing here is actually here the die here. If you look at the ratio of the die to the PCB, it's like 10%. It's not particularly great. Also all the heat, if there is heat dissipation, actually has to travel through the lead frame here. So the longer the distance between, let's say, the tie point and the PCB and the die is actually added thermal resistance here. Not perfect, the SMA design, and actually also the height here is fairly high here. So that's also not so perfect here. So you look at a package like SOD123W, immediately you see it's better. The ratio of the die to the PCB is much better. The heat, or the distance the heat has to follow the die to the PCB is much lower, and the height is also much lower here. So 3 advantages of the SOD123W here. The SMA, by the way, is still a better package probably for wave soldering. So if you're wave soldering, so it's not that the SMA is going to die out. It is not. But the new package is, from a transient thermal perspective, much better, and also thermal resistance perspective, much better here. So that is, further highlights here of products which we introduced, and this actually is something you can think about whenever you use a package choice. If you can get the same die in a smaller package with a TVS, and you have a single pulse surge, then actually it will work out, and the performance will be similar in your design. There is, however, a but here. So the transient thermal impedance actually is important for, let's say, everything around about 1.5 milliseconds. It depends a little bit on the die size. It's 1 millisecond or something like that. But all those ESD and also those lightning strike pulses or short automotive pulses actually are all dissipated in the die. So if you take a die, SMA, you put it in a smaller package, you're done, you're fine, you're okay. However, the thermal resistance of these packages is a little bit more complicated here. If you look at on a standard footprint, the contribution of the PCB is usually like over 80%, and of the package is 20%. So if you improve the package, it doesn't really make that much of a difference, especially since that if you make things smaller, in general, they are actually, the thermal resistance is going to go up because you have smaller solder pads, for example, here. So this is something you have to take into account. On occasion, if you have steady state thermal resistance and that type of steady state power, these new packages are not always that advantageous here. Something that you may want to figure out here. We've seen people actually in a recent webinar of our competitor here actually using SMA and SOD123W components using thermal vias to prove the point. So you can if you want to, but that actually is maybe not the realistic scenario here for those packages. The next slide, I'll pause for a second here, and you can see it yourself. I don't think the TVS product portfolio will change a lot here in the next 5 to 10 years here. It's been pretty stable. The bulk of the business is on SMA, SMB, and SMC, and those can cover from 400 watt or 300 watt all the way to 5 kilowatt here. The actual packages in the beginning on the left of the slide, obviously you will all understand that those are not future runners here. SOD123W is a meaningful addition to the product portfolio here for 400 watts here. Thin SMA and SOD128 are less, meaningful additions, but they are of course contributing to the product portfolio. And then you have the SMPC. If you move here to the third from the right here, SMPC, also called TO2677, TO277, repeating the part name or the package name here. This actually does 1.5 kilowatt here, and it's a smaller or offers a significant footprint savings over the SMC device. So that is a new product here that could be, or was introduced a couple of years ago, but that could be a good contribution. The DO218 or the low down package here with this awkward big clunky copper slab here in the back here is of course for longer load down pulses, but you can see that it's also in other applications we see it used at the moment here. The other one, the only one we're going to add here is the D square pack. Not the perfect packet for load dump, but sometimes sufficient and cheaper than the DO218 AB. So it will have a niche in the market here, even though from a transient perspective, it's not as perfect as the DO218 here. So that's our product portfolio, and I think it will not change that much in the future here. The next slide actually here looks at the packages here, SMA, SMB, and SMC in the middle maturity, and also are definitely more than 30 years old. The low down package was introduced like 25 years ago, the DO218 AB, so it's already that old, so it's not new anymore, I remember it. And of course, the new package, the SOD123W, is going to be the main runner. And of course, there are smaller packages like SOD323, who may long-term also have an influence on the TVS market, if we can solder them like a rectifier. Next subject is we're going to go to automotive pulses here, and I circled it in red at 400 milliseconds here because it is a little bit more complex, right? We mentioned here that the shorter pulses, 820 to 1000, are predominantly die driven and things like that, and of course how the die is attached, right, with a good solder joint, no solder voids or anything like that. Then you'll have a very good, performance here. If you go to 400 milliseconds, obviously the heat spreads through the package here, but it doesn't spread that much that the PCB becomes the more dominating factor, like in the steady state environment here. So it's really complex, somewhere complex in the middle. And this, if you look at this package here, this the load down package here, and this big copper clamp, you think it's a bit clumsy, and a lot of people think soldering it is not that great either. But it is the perfect package for this application. So that's why we're doing it here. And here, of course, what we're seeing here on this slide is we're comparing ourselves against the competitor here. We are on the left here, and the competitor's on the right here. Here, of course, the package design and how things are done, solder thickness, that type of stuff, right? This is all important here on the performance of this device here. So here you can see that the device is usually characterized at a 10/1000 pulse or 1 millisecond, or also on a 10 millisecond pulse here. But the real conditions are a bit away from that here. So do the same data sheets here may actually give you a different performance here. So that's the message we're actually trying to say for this device here. Sometimes designing with this is not so easy. So we actually have an application note, AN1003. The link is there. You can download it from our web. And actually this helps you, and this is just one graph from it, and I'll just briefly explain this graph here. And we have all the 3 load dumps and characterized also for different conditions here. So what happens here, if you have a load dump here you see, let's say, the 19 volt load dump here, then you have it lasts 40 milliseconds, then at least you have to have around 0.6 ohm in series with the load dump, a series resistance here for it to work. If you go to 220 milliseconds load dumps here, you need about 0.85, 0.9 ohm resistance for it to work. And then if you have here the full 400 millisecond load up here, you need a close to 1.1 ohm in series to actually make the device survive here. So this is helping you, and that together with our testing here, we can help you select the right load up protection for your application here. If you give us the norm, the pulses, the voltage, and the pulse length you have to protect against. The more complex one is the centralized load up, the 5B test, as we call it, test B here. I'm putting it here on the left here, where actually the voltage is centrally limited to 35 volt here. So here, here again, the data sheet is not characterized necessarily for such long pulses here. So you may have a difference between us and competitor B or competitor A still here, in performance here. So testing is necessary. The data sheet may not give you all the information you need. The second thing here is, of course, that the internal resistance and actually the distribution is very critical here. So here in this case, 5B here, it's very critical to understand that this is where the biggest cost savings potentially are, or the biggest differences between suppliers potentially are. I'm going to give you actually an example here. So you have the 5B pulse limited to 35 millisecond here, and here we're testing it with 400 milliseconds and internal resistance of 0.5 ohm here. So you would never expect a P6 to manage this, a 600 watt device to manage a centralized load down. But if you can push up the breakdown voltage here, which means a higher clamping voltage here, but potentially the device doesn't heat up that much. It's not that much higher here. So actually here a 600 watt can actually pass here. So this is an area where we can actually work together to save some money, because they are more difficult to predict the centralized load down, the 5B pulses here. They depend a little bit on the distribution of the TVS, how far, if it's only 35 volt, how far is the TVS from the breakdown voltage will have an impact on the length of the pulse here and how much energy depends it. They're very dependent on the internal resistance. And of course, you can have multiple packages here that pass here. So actually, in this case, testing and cooperation with a supplier makes sense to choose the optimal part. Then maybe a small fun interlude here. When I was young, I used to have a chemistry lab as a teenager, and I used to blow up things, or actually make a lot of smoke on Wednesday afternoon. I understand that that's not everybody's hobby, and maybe it's not your hobby in your new beautiful lab here, but let's face it here. Sometimes these destructive tests are necessary here. So here what we did here, and if you need them or if you want to cooperate them, we actually do them for you. So you don't have to put the smoke in your own lab. We actually can give you certified reports here from our lab here, so you don't have to smoke up the thing here. What we're doing here, just this is one of last week, we're taking an SMA in a load dump here, in a full load dump test here. Of course, that never works, so we're destroying it, but we're destroying it on purpose here because we did identify that it could do 95 watts at 35 milliseconds here. So destructive tests can be helpful for certain pulses here, and we actually support them here. Just a little tip here, on the bottom here, you see the TSC clamping voltage at a very high temperature here. So, sometimes you see, we also can supply this thing also on demand here. If it's not, some of our data sheets have the temperature coefficients, some of them don't have them. We can always supply them upon demand here. But, obviously the question is, as these things in pulses here go well over 175 degrees C, what is going to be the real clamping voltage? What's going to be the real junction temperature? It's not so easy to determine sometimes. Here, what you see here, this on the scope plot here, the blue thing is actually the clamping voltage, and it's got a serious bump here, and that is actually the temperature coefficient of the device here at a very high temperature here. So if you see that bump like that, it's starting to get close to destruction time for the TVS. That's a very large gap or increase of the clamping voltage here. So that's something you need to, as a tip here, for you to understand when you're close to blowing up a TVS here. So this is things we will actually work for you and help you with if you want to in our labs, in our factories here. So TSC enjoys testing TVS systems like us. So that's what we like to, destroying them. So that's what we like to remember. What is happening here? We are introducing bidirectional low dump devices. By the way, we say low dump. It's not that these things are in the past when alkaline batteries disappear potentially from electrical vehicles. We're seeing a lot of things in electrical vehicles like circuit breakers or e-fuses and that type of stuff that have fairly long pulses with high energy. So this device is not at the end here. So there is certainly some life in long-term demand for those devices here. So these are the ones with the copper blocks here. You would say, hey, low dump is a unidirectional device or a unidirectional pulse here. So unipolar pulse here. So why do we need a bidirectional device? Well, even in a case where there's a low dump here, there sometimes are negative pulses here. And coordinating with the other protection elements may not be that simple. It may be easier for you to have a bidirectional low dump device. And that actually is what we're now offering here. It also offers some savings from a system design here. So this is something which we are offering to you and what we are doing now. And that's actually fairly new. We also released those in the last couple of weeks. Actually, I took a screenshot from two graphs of our device here. This is where we have both graphs available. We talked about the derating curves, right? So if you use this as a steady state product here, it derates here 8 watt. It's of course going to be on very big solar pads here, but it does derate like a standard semiconductor using a steady state here to its maximum junction temperature. If you have at 10 milliseconds here, you can see the device has 5.2 kilowatts here. And actually, if you move that here for a low dump here at 175 degrees C, it just has around 3 kilowatts left in it. So that is just also gives you an idea. Of course, if you do 3 kilowatts at 175 degrees C, there's going to be a serious, of course, the junction temperature is going to be exceeded here. So both graphs here, the single pulse graph and the steady state graph, are in this data sheet. That happens rarely, but we're doing it in this device here. Let's talk about the snapback TVS diodes here. So I'm doing power management or power semiconductors now for 35 years. And I always say when I talk about rectifiers of TVS, it's a PN junction. It was so 35 years ago, and it will be so in 35 years. But somebody came up with a smart idea with a bipolar structure, and it's called the low current TVS here, which we are introducing now here. So what happens here is that the red line is of course a standard TVS diode. The blue line actually is the foldback device or low clamp device. So you have a secondary breakdown. So you have the first breakdown here, secondary breakdown, and then it outsides like the resistor here. So two great things about it here. First and for all, the clamping voltage is going to be much lower than with the conventional TVS. So for the same current, you're dissipating much less power here in the silicon here. So you can either have a smaller device here, a smaller diode, or you can actually get a much higher current rating with the same device here. So this is the first advantage here of the device. And of course, it has a lot of, the second one is, of course, it has a lot of downstream savings here. What happens here is normally you take a 24 volt, 27 volt here, and everything, for example, in automotive is 40 volt rated because that's what the clamping voltage says here, and that's what you want to do. You don't want the MOSFETs or the ICs, power management ICs or whatever is in there going avalanche or anything like that. Obviously here you can get a lower clamp voltage and you can use lower CMOS behind the TVS here. I think it's in this case you can securely use 30 volts here. That's what the device is doing here. And so as a result here, so what you do get here is that the 30 volt MOSFETs are obviously better than 40 volt MOSFETs, and so are other things. That's the way silicon works and CMOS works here. So this is two advantages of this new technology here. Potential applications are we start with automotive 24 volt here. We may be looking also at 48 volt devices here. It's going to be a little bit different than a TVS. We're not going to introduce thousands of part names here. We might put some standard TVS in series with this device for some applications here, but this actually is the new technology here briefly explained and the two advantages of it. Let's look a little bit more at this technology here. Here is one characterized here. So both here, the first package we're doing for this snapback here is also going to be in the 214 here. And so this is the bidirectional here, which is of course in this case in blue, and the standard low dump TVS is in green here. The bidirectional device by nature, the the snapback device is by nature bidirectional here. So what you're seeing, two things here. You see the clamping voltage being much lower here because of the fallback device here, and also you see that the thermal resistance, the dynamic resistance here of this device is actually, of the snapback device, actually much lower here. So the snapback device has a dynamic resistance of 7.5 milliohm. The other one has a dynamic resistance of 23.4 milliohms here in this case here. So that you know, the combination of the lower dynamic resistance and the fallback features here produce a much lower clamping voltage of, let's say, 1.5 to 1.35 here, the lower clamping voltage ratios. Second thing here is that actually the device is more stable. Again, blue, the snapback device, green, the standard low-level TVS topologies here. The variation here for the snapback device is half of the variation of the standard TVS technology here, which is another advantage here. It is also non-linear. That's something we also need to mention here. So this is another advantage. So this is the first part we are introducing here. It's going to be available in December, but we also are sampling it to a lot of customers at the moment here. One thing I should say here, also future potential here, so it's 7.7 kilowatt here. Things I've seen measurements where at 820 pulses here, it can handle actually close to 3000 amps here, which is actually very close to, let's say, the performance of a GDT. So, you know, it does have also a very high capability for short pulses here. So this is something you should really also understand here. We're going to market this also in smaller packages, but not at hundreds of voltages, a few voltages here, and then series, you know, considerations with standard TVS technology here. We think this is a good technology for the future and has a lot of potential savings here. And I think you'll be hearing a lot of this for the future designs here. We finished the TVS section with 2 slides about applications here, or 2 or 3 slides about application here. We see a lot of applications here going to higher voltages here and not getting enough power out of the standard packages, or we see a lot of people actually being limited by 5 kilowatt and wanting more, for example, in more manageable packages like SMC or something like that. You actually hear, and a lot of the application notes on the web have disappeared, so that's why I'm just mentioning this briefly here. You can put TVS in parallel and you can put TVS in series. The way it works here, if you put them in series, they all have the same current here, and they might have 2 different clamping voltages here. And if you put them in parallel, they have the same clamping voltage, but the current maybe not be evenly divided here. How unevenly actually is determined by the distributions from breakdown voltage and clamping voltage here, and also the dynamic resistance here. But as you can see, those distributions are very tight here. So actually it's not really adding 1 and 1 is 2 here, but it's close here. The derating, you know, doing this is minor or low here. So putting TVS in parallel series is a valid option if you are linked or limited in voltage and in power here. Also here, obviously, is that we have in our data sheets a 10-1000 characterization here. At 820 pulses here, the dynamic resistance of the device is different here. So if you are using pulses like that and want more information about that, the 820 characterization is available from us upon request. Last slide about TVS here is the map of the world, the lightning strike map. I always like to mention here that TVS diodes are actually anarchist here. So we have normed them, and that's great here, but they do whatever they want to the lightning strike here. So if you're exporting to places like Florida or Singapore, to mention the 2 names here, or if you're actually located in those areas, you know, you may see that your lightning strikes are, first of all, more frequent, but also more powerful or something like that. And then you're actually going to see actually the data sheet, or, you know, the die size of each different supplier here in the field failure rates and that type of stuff. So it is possible to have field failures with TVS diodes because the lightning strike actually does not always follow the norm here. So that's something to keep in mind. Let's go to the second part of the presentation here, and we're going a bit faster here through this bit here. It's about ESD, Zeners, and the front end and the supply chain of our components. So what we're seeing here, first of all, let's talk about ESD here. So this is just a slide and I'm not going to go through it because this is you know, an eye chart here. So we're having the whole range of TVS diodes, and we have a few ESD parts here. But we think we cover all the major applications here. We're adding this slide just for completion here. We're going to talk a little bit more about how you can correct or choose the correct ESD components with using our products here. So the ESD, you know, actually there's a few important, you know, famous interfaces, USB, HDMI, that type of stuff. A couple of other ones you want to protect against here. And so the product proliferation actually comes historically and from the package perspective here. So we have also in the past ordered, you know, made SOT23s and SOT26s here. We continue to offer those devices here, but obviously these are the older parts here. We've introduced all our new parts, or most of our new parts, are DFN packages here. If you look at it, you know, if you remember from earlier in the presentation when we compared the SMA and the SOD123 and the length of the lead frame and that type of stuff, you know, these things don't have any actually thermal dissipation in them, but in this case, the lead frame, every extra millimeter, of course, is inductance here, and that's undesirable here. So that's why these DFN packages are offering you an advantage here for ESD, and that's why we, of course, think they are the growth area for the future. Capacitance here, I like to make one or two slides here because it's not always very well understood here. TVS also has a capacitance here. We're taking a 1 kilowatt TVS here on the right-hand side here. You know, the junction terminal, that's a 1 kilowatt in SMB package here. And I'd just like to understand this graph before we go to the ESD graph here. Capacitance is defined as the permittivity divided by A over D. Those are two plates here, capacitance here, and a distance here. You know, can be air gone as well, right? The permittivity of the electric here is that. In a semiconductor or a TVS, actually here, the A is a die size, or if you want to be really correct, it's the active area. That would be the most correct way of saying it here. And the D is the depletion layer, which is voltage dependent here. So if the in this case, if the voltage goes up, obviously, you know, the depletion layer actually also widens, and so that one here actually here, that's how the D is on the reverse side. So that's actually how you get the capacitance to go down as the voltage goes up here. So the voltage goes up, the depletion layer goes up, so the capacitance goes down, or D goes down here. So that's actually also here. Let's say go to this graph here. Let's take the 100 volt TVS here. If you have no voltage here, then the depletion layer is smaller as you start to apply voltage on that 100 volt TVS diode here. You know, the depletion layer also here increases here, and you've got the capacitance going down here. And then here, if you go for, let's say, from the breakdown voltage 10 to 100 volt here, you're starting to have a different, you know, material resistivity here and a different dielectric value here. So that actually makes the thing here change here to here, or not the dielectric silicon, but you know, the voltage here dependent on that here. So that actually explains to you how the capacitance curves here work on a semiconductor here. Obviously, the smaller the die here, you know, the lower the capacitance here. That's what you want to do here. So if you want a lower capacitance, you go to a smaller die size. But it has limitations because in the end, it can no longer handle the pulse, the power here, and it breaks down here. So there are limitations to it here. So that's what you do here. For example, on interface, you have the bus here, and the power line here, and the data line, which have different what we call requirements on the capacitance here. Capacitance here, of course, being insertion loss, and the 0 and 1 being distorted and no longer being recognized because of the capacitance of the TVS here. So what happens here is you put a TVS line in series. You put a small capacitor in series with the TVS here. There is a thunderstorm, and if the electricity fails in Portugal, there's nothing wrong, we will record it, but I will continue here because we just had a power interruption here, but it seems okay. So the bus line actually here, traditional Zener processes here can work correctly here. On the data lines, there are lower C products, capacitive products are needed here, and actually to make them, you need complex CMOS processes. So to put these steering diodes in series is not that simple here. And also you may actually have many data lines that are multiples of 2 or 4, allowing you to integrate them in a package here. You have a different interface, USB or HDMI, which has a different maximum capacitance or insertion losses here. And also those ICs here, because I'm going to call them ICs because they're not simple Zeners anymore, have non-linear capacitance here. So that is the area, and the main message is actually those low capacitance products actually here are complex CMOS ICs. That's what I'd like to repeat from this message. Our marketing people made this here. So the main thing, if you are selecting here, is check out the capacitance here. And then here, of course, you have, we have solutions for all applications, USB, HDMI, but also the smaller ones like some audio applications here, or some older inputs here, or USB 2 or that type of stuff. So each one has a maximum capacitance they allow, and then if you're under that capacitance here, you'll probably have acceptable performance here. So that's the best way actually to look at your selection for ESD protection here, and we can help you with the details on that. I'm going to take one thing here just to get an idea about this capacitance here. We got two parts in this 2510P10 package here with 4 IOs here, more aimed at HDMI type of applications here also. And what we see here is one has 0.8 picofarad, the other one has 0.28 picofarad. We're comparing apples to apples, or not 100%, but close to 17 kilovolt. And 12 kilovolt ESD versus 15 kilovolt and 10 kilovolt here. So actually, the lower, of course, the thing here, the requirements here, the smaller you can make the die here. So, but there are two other things that help this technology here. The first one is, of course, again, the snapback technology here. What it means is here that for the same power, you're dissipating less energy here, and you can make the die smaller here, and also reduce the clamping voltage here. And of course, a bidirectional device has two capacitances on 0. This one is actually bidirectional, and this one is unidirectional. So the bidirectional device is two capacitors in series. That means you halve it, or close to half it in that case here. So there are tricks here to further reduce the capacitance here, but we are getting close to the limit here. And actually, these ICs are no longer complex to make, or no longer easy to make. They are actually very complex. We can provide eye diagrams for all these products here. They are not available in our data sheet, but we can provide them to you upon request here. That's another major issue I want to tell you about our ESD capabilities. Last couple of slides here. What is the difference between a Zener and a TVS here? A TVS has a much bigger die than a Zener. The back-end assembly is much more robust to handle short pulses. So it is soldered, and it also maybe is not wire bonded, or doesn't have small wire bonds here. So this is the main and key thing here, and is again related to the beginning of the webinar: transient thermal impedance versus thermal resistance here. So that is the key thing here. And I just took some Wikipedia drawings here. I don't want to insult any supplier or anything like that, but these things are actually pressure contacts, the dime here with the copper slug here. These are pressure contacts here, and whatever the die adhesive here, sometimes they're not soldered, and this also may be, or the small bond wire may be problematic for surges here. So some people actually see Zener failures when there are pulses here, and that is usually for two reasons here: a small signal product followed by a capacitor sees a small surge. Maybe this thing is not characterized for it. This is the first thing here, and there also may be what we call residual energy. Residual energy means that there is primary protection, where actually the signal that is destructive signal comes into your package. And actually, when the package, and the TVS actually reacts there, but there might be a difference in voltage level or anything else later on in the circuit here. That's what we call residual energy, and that actually from the surge, and that actually can also reduce a Zener diode here. So these are two failure modes with the Zener diodes that are well known and popular, or not popular, well known, I should see here. So sometimes you do need power Zeners to actually mitigate from them here. Power Zeners also have their unique applications here. Sometimes, for example, in half-wave rectification here, or very low power supplies like 1 watt or 2 watts, you use a power Zener here at 1 milliamp or 5 milliamps or something like that here. But if those things have 40 volts or 50 volts here, then you are still getting a significant power dissipation in the package here, and then you need a real soldered package with a good package construction here. Our Zener portfolio is also added for completion here. On the left-hand side, you see the ASCQ qualified products here, SMA, SMB, and SMC, which are sold regularly here, and also SOD123W, which is also a very good package here for power Zeners here. They are here in 1,000 milliwatts, or as you said, the 1 watt or something like that here. Here is what all those packages are, the traditional Zener packages here with lower power ratings. Final slide here, between the supply chain and the front-end processes. This year is relaxed here, but 21, 22, maybe we won't forget them, but we had long lead times and that type of stuff. So I always keep one slide at least for the supply management, so you get an idea of what you are buying and how these things are made here. So we have 3,500 or more TVS part names. So, and actually we're selling also these voltages, you know. Sometimes some of them we sell in the millions, and sometimes we sell in the 10,000s, you know, but we sell them all here. So the GPP process, or the glass passivated pellet process, is the dominant process in this area here. It is cost efficient, and it has a smaller wafer size, 4-inch, 5-inch, that type of stuff here, typical in the industry here. You can actually use planar process, of course, also to reduce TVS. They are more complex and more expensive processes here that can actually also reduce the die size as on the other side here, but they are more complex processes here. And actually, I would say that, you know, if you're using planar, you may use like 8-inch wafers or something like that here. You know, if you have 3,500 part names, that is maybe not an advantage here. So that may actually give you also some on these bigger wafer sizes, may not be an advantage in the supply chain and on lead times here, especially on the alt voltages, maybe not 5 volts, but maybe on 51 or 93 volts or something like that. That is definitely not an advantage here. Part names can be covered with most applications here. Some suppliers have lots of part names here, but I think that's mainly because of package proliferation here. You may not need that type of packages here. There, of course, is a shift in packages, which is determined by the layout and inductions, and you know, TSC will add SOD523 because that is a small package here, but most of our developments are now in DFN packages here. Whatever you do, don't forget you are, you know, buying a complex CMOS process here in the front end, and you know, it's not that you can change your forecast within a week or 2 weeks and should hopefully get support in this case here. No, those are actually complex processes here. So I think we passed the 45 minutes by 2 or 3 minutes. I apologize for being 2 or 3 minutes over delayed here. But in this case here, if you have any questions, I will now happily answer them. The slides will be shared. I see that somewhere. Yeah, there you will follow an email here, and the slides you will get the slide here. So that's the first question I see. Sometimes these questions are not always visible for me. I do apologize to look at the chat. So I'm trying to see if there are any other revisions. I will wait 1 or 2 more minutes to see if any further questions come in, and then we will close the webinar. I think I see no further questions. So in that case, I would like to thank everybody for their attention here. We will be contacted with a follow-up email, and I wish you all a pleasant afternoon, or if you're in a different time zone, a pleasant day. Thank you very much, and goodbye.